My name is Thomas Rokicki, and I'm going to tell you how I solved the orchard problem from this year's North American Championship. The apple orchard problem gives us a set of circles and a set of rectangles. We're supposed to answer for each rectangle what percentage of it is covered by at least one of the input circles. We want to pre-process the circles in some way that lets us answer the queries about the rectangles rapidly. The boundary of a region that is comprised strictly of circles is just a set of arcs, and it is exactly those arcs that are not covered by some other circle. So we want to calculate the set of arcs not covered by some other circle. If two circles intersect non-trivially, meaning one's not entirely within the other, then each covers some continuous arc of the other. That arc can be represented by an angle interval of the angles covered. In order to keep our angles between negative pi and pi, we may need to split such an interval into two if it crosses the negative y-axis. So for each circle, we can make a list of the arcs of that circle that are covered by some other circle. The basic circle-circle intersection code, if you don't have it in your book, it's fairly easy to do just by taking the distance between the centers of two circles and their radii and making triangles and then using simple analytic geometry. So what we want to do then is for each circle we have the set of arcs that are covered by some other circle. We want to take the union of these arcs and subtract it from the original circle to give us the remaining arcs. How do we do this efficiently? We simply sort the intervals that are covered by the first component and then scan from the beginning to the end. If two adjacent intervals are mergeable, meaning that they overlap, then we combine them into one longer interval and continue. Otherwise, there's a gap between our current interval and the next one in the list. That gap is exactly an uncovered arc, and we want to save those. So we do these linear scan, merging adjacent ones, and store away the complement intervals. Now, how many arcs might we end up with at the end of this process? It turns out there's going to be at most 6 times the number of circles arcs, even though any particular circle might intersect with every other circle, and indeed the count of boundary arcs from an individual circle might actually be as high as the number of other circles minus 1. In addition, there's n squared intersection points between the circles potentially, but rest assured at most 6n are going to be on the boundary. So our eventual representation is linear in the number of circles. To simplify later processing, once we've got each arc, we split any intervals of that arc that span the pi over 2 or 0, because this means that each arc is monotonic in both x and y, and that just makes our calculations later easier. We also calculate the bounding box, lower left and upper right coordinate pairs, and we also calculate the quadrant that each arc is in. And this tells us what direction each arc is going, which helps us, again, later do our arithmetic. To calculate area within a shape on the plane, we only need the boundary segments. But interestingly, we don't need the boundary segments in any particular order. We can actually calculate the boundary segments completely independently of each other and just sum it up. And the way we do that is we take each segment and we project it down to infinity in the y direction. And then we intersect that with our rectangle, which is going to make it finite or 0. Another nice feature of this problem is the direction of each arc on the boundary is given by the direction of curvature. If it's curving down, that means it is an upper portion, and if it's curving up, that means it is a lower portion of our area. So now how do we process queries? For each query, we simply walk through the boundary arcs in any order and calculate the area contribution due to each. How do we calculate the area contribution? Well, there's a lot of different ways to do this, and how you do it can really help you solve a particular problem effectively. In this case, we choose a reference line that is the base of the rectangle. By choosing this as our reference line and considering the intersection of the arc projected down in y, we realize that any arc that lies completely to the left or completely to the right or completely below our rectangle does not contribute any area at all. And there are other simplifications that are made by this, so that's really nice. So here's an example, and you see the rectangle and you see the different arcs. They're in black from all the different circles. And this arc that's all the way on the left here, that arc doesn't contribute anything to the area, because when we truncate the area of that arc when we intersect that arc and its contribution to the area with the left side of the rectangle, we end up with the null set. So again, any arc that is completely under, the left of, or the right of our rectangle contributes nothing. We use the bounding box for that. If any portion of an arc lies to the left or right of the rectangle or below the rectangle, we can simply truncate that portion of the arc and work only with a shorter arc. Now, if an arc intersects the top of our rectangle, then we need to split the arc into a line segment that is part of the top of the rectangle and any remaining curved portion that lies completely within our rectangle, and we add those areas separately. So that's the whole thing. It's a little bit of geometry, but the geometry works out fairly easily in the end, and the pre-processing considered only n-squared circle-circle intersections. We did have to sort, so the total pre-processing complexity is n squared times log of n. The query step iterated through O sub n arcs for each of the q queries for a total complexity of nq. So our overall complexity is n times n log n plus q. I hope you enjoyed this problem. It's challenging to get this problem exactly right because there are a lot of cases with these circle line and circle rectangle intersections, but if you're careful and you choose an appropriate reference point for adding up the area, things work out much more simply than they would otherwise. Thank you very much.